Thank you very much. So I would like to thank the organizers of this wonderful program. It's a big pleasure to be here. So I realized that not only the title of my talk, but also the Beamer theme of my slides are very similar to the previous talks. So in fact, Alexander Bobenko and his co-author, they come from geometry and became interested in dimers. With my co-author, David Cimasoni and Béatrice de Tilière, we were interested in dimers and get interested in the geometric aspects of it, and somehow we met somewhere in the middle. So many things I will tell today have some overlap with what Sasha explained before. So I would like here to report on some series of papers we wrote with David and Béatrice on this topic. The last one was 2 years ago about this minimal dimers and maximal surface. And I would like to start with some motivations, but since Sasha explained many of the things, maybe I will have time to say a few things about new results on Laplacians on the graph we are considering. So a few words about the motivation. So we already saw several times during the week this question of looking at dimer models on biperiodic graphs. So we start with a periodic bipartite planar graph with periodic weights. And the work by Kenyon, Okunkov, and Sheffield was to classify all the ergodic Gibbs measures that would give, when you condition the configuration outside of some bounded region, to give the Boltzmann measure on this finite graph with the weights you are considering. So they showed that this classification can be done by looking at what is called the characteristic polynomial of the dimer model, which is the determinant of the Fourier transform of the Kasteleyn matrix. And you look at the zeros of this Laurent polynomial in Z and W. It gives some algebraic curve in the plane. And so what is important is the amoeba of this algebraic curve, which is the image of the coordinates by the logarithm of the absolute value. And this amoeba plays the role of a phase diagram for the dimer model. And there is another object which is important, which is the Newton polygon of the characteristic polynomial, which is the convex hull of the powers of Z and W, which has a non-zero coefficient in the characteristic polynomial, which is somehow dual to the amoeba. So how their result look like? It can be formulated as follows. So once you fixed the weight, all the ergodic Gibbs measures are in fact determinantal processes on the edges of your graph. So it means that if you look at k different edges connecting a white vertex Wi to a black vertex Bi, for every I between 1 and k, the probability that these edges are dimers is given by this formula. So you have the product of the Kasteleyn entries of the entries of the Kasteleyn matrix corresponding to the edges you are interested in, times the determinant of some matrix, and this k by k, so it's a k by k matrix, and the coefficients of this matrix are the entries of what can be seen as a formal inverse of this Kasteleyn operator from Fourier analysis, but you are somehow allowed to change the radii of the torus on which you you integrate. So you have two parameters, bx and by, which live in the plane where the amoeba lives. And the behavior of this coefficient when the distance between the black and the white vertices increases depends drastically on the position of this point bx, by in the plane. And they prove that there are three phases depending on the position of this point B. So when B is inside the amoeba, so the amoeba here is the annulus between, okay, I don't know. So outside of this blue curve and in the region delimited by the green and orange curves. So it's an annulus like this. So if your B is inside this region, you get what is called the liquid or the rough phase. And in this case, the correlation between edges decay polynomially. If you are in a bounded component of the amoeba, so for example, inside this blue curve here, you are in the smooth or gas phase. And if you are in an unbounded component of the amoeba, you're in the frozen situation, so some edges will appear either with probability 0 or 1. So some things do not, so are becoming deterministic in this regime.
I'm sorry. So in the top formula in the theorem, the left-hand side does not depend on bx and by.
Well, so in fact, so every Gibbs measure has this form, and so this p here is one possible Gibbs measure. So I should have put an index b. So this probability really depends on your choice of p. Okay. So these spectral curves, they play a very important role to understand like, the phases of the model, etc. And the algebraic curves which appear in the Daimer model are very special. They are so-called Harnack curves. But so Kenyon and Okunkov proved that, in fact, every Harnack curve can appear as the spectral curve of a Daimer model, and they prove, in fact, something more precise, which is this spectral theorem, which tells you that if you look at, so that there is a one-to-one correspondence between Daimer models on my biperiodic graph modulo some transformation, and the set of Harnack curves living on the same Newton polygon with an extra data, which is a standard divisor, which is just a collection of points living on the ovals of this curve. So one direction to prove, well, for this map is what we saw. So from the weights, you compute the characteristic polynomial and look at the zeros, which gives you an algebraic curve. And to see the divisor, in fact, what you need to do is to, for example, fix a white vertex somewhere in your fundamental domain of your graph and look at the comatrix of this, the Fourier transform of the Kasteleyn matrix, and look at the point on the curve where the whole column corresponding to this white vertex vanishes. So it gives you a collection of points which play a role to characterize the corresponding Daimer model. But for some time, there was no direct construction for the reverse map. So how to construct from a Harnack curve with a standard divisor, the Daimer models with the correct weights that would correspond to this spectral data. So this was done by Fock 10 years later in an algebraic setting. So there was no positivity consideration about, so he was not very interested in the probabilistic setting, but what he did was taking as an input an algebraic curve with a divisor, and getting as an output a periodic graph and a Kasteleyn matrix, which if you did the construction to get the spectral curve from this Kasteleyn matrix, you would get exactly the algebraic curve you started with, and the standard divisor here would also match the one you used for the constructions. So the entries of this Kasteleyn matrix, they are given in terms of theta function and prime form. So I will come back to this formula a bit later. But what an important feature of this construction is that the square move we saw several times during the week, which is an elementary operation on the graph, is somehow encoded in what is called the phase 3-second identity, which is an important functional equation that the theta function and the prime form satisfies on a Riemann surface. So this is a part of the story describing what happens on periodic graphs. So what can we do about non-periodic graphs? So I want now to consider a situation where my infinite graph is not necessarily periodic, and the question is it possible to, so you can always define an infinite Kasteleyn operator, but the question is, what can you somehow write down a formula for the inverse of the Kasteleyn matrix? Can you define measure in infinite volume with these inverse operators? So there was one example that was known by Kenyon in 2002, which is the case of isoradial graphs. So a way to construct an isoradial graph is to start from a tiling of the whole plane with rhombi, which are the gray pieces here, with side lengths equal to 1, let's say. And I impose, moreover, that, yes, okay. So you start from this infinite tiling. And now I will construct my isoradial graph by taking one point, one vertex of this rhombi, and deciding that, so this will be a vertex of my graph. And then I draw the diagonals of the rhombi, and this will give me new vertices of my isoradial graph. So the vertices of the isoradial graph are every second vertex of the gray graph here, and they are connected by diagonals of rhombi, and they are called isoradial because of the following property. So if I look at the vertex of a rhombus which is not a vertex of my graph, for example this point, well, it is at distance exactly 1 to every other vertex around the face. So I can draw a circle of radius 1, which will pass through all these vertices. So this is why it's called the isoradial. And so I want also my graph not only to be isoradial like this, but also to be bipartite. And Rick gives a formula for something that turns out to be a Kasteleyn operator. So how does it go? So on this graph of rhombi, you can see that there will be like infinite paths, which is these train tracks or zigzag paths we saw before. So they cross, in fact, rhombi which have a parallel direction in common. So all the rhombi crossing the red strand here, they have this direction in common. So what I will do is I assign a parameter to every train track, which is just the unit vector which encodes this direction. So for example, the red will be EI alpha, the blue will be EI beta. And I define the Kasteleyn matrix for this edge between the black and the white vertex to be just the difference of these two unit vectors. And Rick gave an explicit inverse for this operator, which has a very nice property that it's local. So let me explain a bit this formula. So the entry of the inverse Kasteleyn matrix between a black and a white vertex, which may be far away, is computed by first accumulating along a path between these two vertices. So this is a path in the graph of rhombi. I collect these unit numbers and create this rational fraction. With some, these linear factors, they go to the numerator or denominator depending on some convention I will not explain. And then you multiply by the log, you compute some contour integral, and you get a formula. And so since this quantity, in fact, depends only on the geometry of the path between the black and the white vertex, it means that you can change your graph, your isoradial graph outside of this path by preserving isoradiality, and it will not affect the entry of this matrix. So this is a very striking feature.
So you mean, by path, you mean the minimal path, shortest path?
In fact, it doesn't depend on the path you choose. Because so if you, so it comes from the fact that if you
something telescopes, right?
So if you go around the rhombus, if you go in this direction, then in this direction, you collect the same factor as if you would go in this direction.
So it has to cross every zigzag path.
Yes. So yes.
At most once.
Yes. So you can compute it on a minimal path that will cross exactly once all the train tracks separating these two vertices, but you could compute it on any path. Yes, so we were very amazed by this property, and we were wondering, is it something special to these weights, which could be like discrete criticity condition, or is it something more general? Can it be? Yeah. So that's somehow our motivation. So in fact, this isoradiality condition, which was a geometric condition on the embedding of the graph, can be translated as a topology condition on the graph. So you can, when you have a planar graph, you can always superimpose a graph on its dual and draw what is called the diamond graph, which would be the analog of this graph of rhombi. So now you have generally just quadrilateral. And Kenyon and Schlenker, they prove that you can embed your graph in such a way that these quadrilateral are indeed rhombi if and only if your the train tracks you get do not form any of these three conditions. So in fact, it turned out that Kenyon's construction works also in a more general notion that we saw before for not only isoradial graph, but what is called minimal or reduced graph, which is the situation where you forbid train tracks to cross themselves or to have multiple crossing in the same direction, but you allow crossings in multiple crossing in opposite directions. Okay.
So the graph from your first slide doesn't have an isoradial embedding, is according to the first result.
I mean,
from the first, like the very first slide, you had like a little square.
Yes, so it's not isoradial, but it's minimal. Yes, because yes, it's because, okay, could make a picture. So you could embed it isoradially, but some of the rhombi would be like degenerate so it wouldn't be an embedding. So some of the vertices would be sent to a point, or there is a general notion, a more general notion of what we call what's the name again? Isoradial immersion, thank you. That are somehow a way to draw your graph with rhombi, but some of these rhombi would be flipped. So you would get something that is not an embedding, but almost. Okay, so yes. So what we want to do is do the following. So we would like to generalize the setting of isoradial graphs using Fock's formula for the Kasteleyn operator. So how we will do this? So what we want to do is to work with all the infinite minimal bipartite graphs simultaneously and replace, in fact, okay, so this is maybe something I need to explain here. So the situation here is that all the parameters assigned to the train track, they live on well, so this parameter lambda is a complex number which I want to see as living on the Riemann sphere, lambda. And on this Riemann sphere, there is this unit circle, which is where the points EI alpha and EI beta live. And so what we want to do is somehow replace this Riemann sphere by a more general surface. So we will take as a surface, sigma, with some property. So this is something we already saw in the previous talk. We want this curve to be maximal. I will say a bit more what it is. So this Riemann surface will play the role of the spectral curve in the periodic case, but here we take this surface as given a priori, and it will be the same for all the graphs. We choose some extra data, which is a real point on the Jacobian of this surface, and we look at the Fock-Kasteleyn operator on this family of graphs. And what we want to do is define a family of inverses for this operator in this general context, and try, in fact, to read some probabilistic quantities as functions on sigma directly. And you can see this as a way to provide an alternative classification of complexity of infinite planar graphs. So one approach before was to look at periodic graphs, and you say that a graph is simple if its fundamental domain is small, and it's complicated if the fundamental domain is large. But here, the notion of complexity will come from the genus of the surface. So for me, minimal graph will be simple if the surface sigma is, for example, the Riemann sphere or a torus, but the complexity would increase with the genus of the surface. Okay, so what is a maximal surface? So my picture is somehow a bit different from Sasha's picture, but it's the same. So my involution now is sigma, not tau. So I have these curves, which are the fixed point of this anti-holomorphic involution. And I want my surface to be maximal, so the number of components you see is always equal to the genus plus 1. So this is the maximal number you can have. And so I denote this cycle by A0, A1, A2, and so on. So I will use A1, AG to form a basis of homology if you add to them a collection of B cycle, which will go around the whole like this. And you can construct like a basis of holomorphic form, which would be adapted to these cycles, and you need to define a bunch of geometric objects. So there are these first, the Riemann matrix associated to the surface, which is just the integral of the basis of holomorphic form along the new cycles BI. And then from this matrix, since it's the imaginary part is a definite positive, you can construct this infinite series, which is a Riemann theta function associated to this surface. And from it, you can construct the prime form. And the theta function and the prime form, they satisfy this, this identity, which is called the phase identity, which is a higher genus analog of the I hope I get the sign right. This one maybe it's not true. Okay.
Cédric, is it possible to say what is a prime form? Is it too complicated?
No. Well, so you can think of it as a basic object to create meromorphic functions with a prescribed polar and zero on the surface, but I cannot.
Is it determined by that phase secant identity? If I fix theta, is that?
No. No. Okay. So what happens is that the minimality condition on the graphs tells you that there is a well-defined partial cyclic order on the strands. And what we will do is use the cycle A0 I haven't touched yet to put parameters on the train track. So for every train track T, I assign a parameter alpha T, which lives on this cycle A0. And I will need another object which was not present in the critical case, which is this discrete Abel map. So it's you can look at it as a formal combination of points that will live in this particular case in A0 by doing the following. So you start from a point somewhere, and okay, maybe I start from this point. And then every time you cross a train track, you add or subtract the parameter of the train track. You see, depending on the convention that I will not also spend time to explain, but it's a crucial object. And so this is Fock's formula for the Kasteleyn operator. So you have the prime form of the two parameters attached to the train tracks, and you divide by two theta functions, where t is the parameter I fixed on the Jacobian of my surface, and you have this discrete Abel map evaluated at the two faces that are bounding this edge. And a lemma is that if your surface is maximal, the map from train tracks to alpha t is monotone in the sense that it preserves the partial cyclic order you had on your strands, and you chose your extra parameter to be real, then this operator satisfies the Kasteleyn rule. So you can really use it to compute probabilities on your, well, at least to define something that could have a probabilistic meaning in the infinite graph. Okay. So it turns out that you can define functions in the kernel of this operator. So these are the Baker-Akizer functions that Sasha presented in his talk. So they are defined as follows. So you take 2 points, B and W, and again, to compute this function, which depends on this pair of vertices, but also on the point U living on the surface sigma. You look at the path between these two vertices, you collect the parameters, and then you multiply factors which will depend on the parameters and the discretable map along this path. And the fact is that these functions, they are in fact, as a function of u, they are meromorphic one form on the surface. But if you fix u and look at this as a function either of the black vertex B or the white vertex W, they are in the kernel of the Kasteleyn matrix. Okay, so what is the proof of this fact? Well, it's in fact just a consequence of phase 3-second identity. If you look at just one term like this, this identity tells you that this coefficient is in fact something telescopic. And when you will sum either over W or over B around a vertex, you will get something that will sum to 0. So it's quite simple. So from these ingredients, we were able to construct a family of inverses for this Kasteleyn operator as follows. So I define an infinite matrix whose rows are indexed by the black vertices and columns by white vertices. And they depend on some parameter u0, which lives on the upper half of my surface sigma. And how it is defined? Well, I look just at this one form G of BW, and I integrate this form along a contour which will connect, in fact, U0 to its image by this anti-holomorphic involution. So it's some contour. I have to be a bit careful to define where this contour crosses A0, because this quantity has poles along this contour. But you can define it, and the fact is that these inverses, they also satisfy some locality property, because as these functions were defined, like in the critical case, as products of quantities that are collected along a path between B and W, it tells you that this quantity doesn't depend if you change your graph, and in particular if you perform local moves or replace like big chunks of your graph by something else outside of your graph by preserving the minimality condition. And under some technical condition, we can show that indeed, using this locality property, the formula we had in the periodic case, but now when you replace the inverse Fourier coefficient by these new matrices, this defines a Gibbs measure for any minimal infinite graph. And these measures have also 3 possible phases, which depend on the position of U0 on these curves, on sigma plus. So if U0 happens to be on the red curve A0 here, the measure will be frozen. If U0 is on one of the other edges, you get something which is in the gaseous phase. But otherwise, if it's inside in the interior of sigma plus, you get the generic situation where the measure is liquid. So this is a way to define, in fact, simultaneously on all these minimal graphs, probability measures with these local operators. And since the coefficients depend only on the local geometry, it tells you somehow that all these dimer models, they are coupled in a very strong way. So you can, yes. So if your graphs differ just by a finite piece by finite pieces, then this measure will coincide almost for events in depending on not depending on these local places where the graphs are different. Yes.
Just to check the graph on which dimers live, it's in a plane, right?
Yes, it's in a plane.
It's infinite.
It's infinite, and all the faces are bounded, and they satisfy this minimal condition that the strands.
And when you say that it's rough, you mean that the correlation are power law in the distance?
Exactly. So the decay of the coefficients of this matrix are the same as in the periodic case. So they will decay. So, for example, in the rough region, we can show that the asymptotic of this coefficient will be like the imaginary part of something oscillating divided by the difference of a function evaluated at the black vertex minus the same function at the white vertex. And this function is in fact closely related to the T embedding of the corresponding.
But the graph itself is not periodic.
The graph is not periodic.
Right. So it's the Euclidean distance of the...
Yes, it's the Euclidean distance if you draw your plane using the function that appears in the asymptotics of the K-1. So, yes. So, in fact, it's true that the graph we are considering, they do not have any geometry built in because we don't start with something that is, for example, isoradially embedded. It's just some topology of strands, and the geometry appears somehow in the asymptotics of this. Okay. Thank you for the question.
But there's a posteriori geometry that you put on the graph, right?
So if you want, for example, to show that the height function converges to the Gaussian free field, you need to use the geometry which is given.
Which geometry?
The geometry which is given by the asymptotic of this operator. So somehow, what appears in the asymptotic of this matrix are somehow the log derivative of the function g, which were in the kernel of the Kasteleyn matrix. And this function, since g is a product of terms, the log derivative will be a sum of terms, and you can use it to draw the edges of your graph.
Determine the angles in the graph. I mean, the graph is determined by some angles of the rhombi, right?
There is no rhombi, so there is no rhombi. So the quads you get at the end, they are not rhombi. So yes, there is no rhombi. So it turns out that the tools you can use to study the situation in the infinite plane can also be useful, for example, to study a finite graph such as the Aztec diamond. So very recently with Béatrice, we found a formula which generalizes the formula obtained by Berggren and Borodin for periodic weights. So what we do is just, you take the Aztec diamond and you have these train tracks which come in 4 family, and you can like put Fock's weights on this Aztec diamond. So any system of weights on the Aztec diamond is gauge equivalent to a particular choice of Fock's weight, maybe for a very high genus surface. But there is a formula to compute the inverse of the Kasteleyn matrix for this Aztec diamond in this context, written as a double integral, but this time directly on the Riemann surface you start from. And you can use it to study asymptotic by just reproducing the steepest descent analysis that Thomas and Alexei did in their paper. So for example, here I drew what would be Arctic curves corresponding to settings that are not exactly contained in their paper, but which should be obtained also by your technique. So this is a 2x3 periodic case, but with critical weights. So if you had generic weights, this would be a genus 2 surface, but here you get something which is just a single rational curve. And this is a situation like the quasi-periodic situation that Sasha mentioned before. So you take periodic parameters for so all the alpha, beta, gamma, and theta are the same. But as Sasha explained, this doesn't mean that the weights are periodic, but they are somehow almost periodic. But in this case, you get a limit shape which looks like this. So I have 10 minutes, right? Okay, so I would like to say a few words about how to generalize this setting to Laplacian, because in Rick's paper on isoradial graph, he was treating not only the inverse of the Kasteleyn operator, but also the inverse of the Laplace operator on these isoradial graphs. So we would like to see how much content can be extended to this setting. So the Laplace operator is just some operator acting on functions on the vertices of my graph. So I will have positive conductances for every edge on my graph, and the Laplace is just this the weighted sum of the increments of my function around at all edges at a given vertex. So a few years ago, Terence George proved an analog of the spectral theorem for biperiodic planar electrical networks, which is a bit imprecise here, but which says that morally you have a bijection between biperiodic planar electrical networks modulo elementary transformation and Harnack curves with even genus, some additional involution which comes with additional involution, and a divisor which lives now in the what is called the Prüm variety of this Harnack curve. So this additional involution can be understood as the Fourier translation of the fact that this operator delta is symmetric, and somehow the fact that this Harnack is characterized by the fact that this operator is positive somehow. So he was also able to perform the analog of Fock's inverse construction by giving explicit formulas for conductances when you start from an algebraic curve in terms of new theta functions, these Prüm theta functions. And the interesting fact is that when you do elementary star triangle transformation on the graph, the way conductances are transformed is somehow built in this Fay quadrisecant identity, which is an identity satisfied by the prime form and these Prüm theta functions. So it's very tempting to try to reproduce the construction we had on dimers to the case of infinite like Laplace operator on infinite minimal graphs, let's say. So what would be the geometric setting in this case? So you get a maximal surface of even genus. You have still this anti-holomorphic involution, but now we have this new holomorphic involution tau, which is like this, which in the case of algebraic curves is this inversion of z and w to 1 over z, 1 over w. So you want these two involutions to commute, and you want also that when you quotient this surface by this involution tau, you get a new Riemann surface which has a genus G this time, and you want this curve to be also maximal. Okay, so this is the starting point of the analysis, and you have some parameter E, which is like the analog of the divisor in Terence theorem. And you could start building, but it was interesting for us to look at the relation between the Kasteleyn operator and the Laplace operator. So there is this temperless bijection between spanning trees on a graph and dimers on the medial graph, which the medial graph is obtained as follows. So if I have an edge of my graph G, I just put a white vertex in the middle. I look also at new vertices which correspond to faces of my graph. I connect them so that this white vertex is degree 4, and this gives me this medial graph. And it turns out that asking for this dimer graph to be minimal means that G has to be to satisfy the topological constraint that it has an isoradial embedding. So it satisfies this Kenyon-Schlenker condition. And in this dimer graph, all the train tracks which were appearing in my initial graph G now are double, but with opposite direction, and I assign them some parameters, alpha and alpha prime, where alpha prime is the image of alpha by this involution tau. Okay, so on the square lattice, not only we have a bijection between spanning trees and dimers, which tell you that somehow the determinant of this operator are related, but also we have in fact a direct relation between operators. So if you choose correctly your Kasteleyn weights on the square lattice and you compute the product K star K, you get a block matrix, a diagonal block matrix where you read the Laplace operator on the graph and the Laplace operator on the dual graph. And it turns out that in this general setting of isoradial graphs, if you modify slightly George conductances, you can find a gauge such that the Fock-Kasteleyn operator transformed with this gauge that I denote by L satisfies the same identity. And what is important is that this gauge transformation, they can expressed in terms of local parameters around the white and the black vertices. So it's a very, very nice feature. And so we can construct in this setting the green function. So it's very similar to Kenyon's construction in the isoradial case. So you first define a family of special harmonic functions which are related to the function G we had before with the same gauges. And it turns out that these functions appeared in some like problem of discrete geometry studied by Doliwa 15 years ago, something like that. Then you need to, for every vertex, to define a one form, which also depends only on the local geometry around this vertex y. And you can write down an expression for the green function, which will be, again, an integral of this harmonic function times this one form along some contour that will connect 2 points on your surface, which turn out to be the two fixed points of the involution tau. And you can see that this function will have the correct behavior as expected for the plane grid function, and that this green function satisfies some locality property. questions about this formula? No, so okay, so I have maybe a few questions, open questions, and I can ask. So we studied with Béatrice and Kenyon Rachel an Ising model on isoradial graphs, which turned out to be connected to the Laplace operator with elliptic conductances. So it would be interesting to look at the corresponding Ising model on these isoradial graphs in connection with these Laplace operators. In fact, so what we are able to say is we can provide families of inverses for these infinite operators, but there are many ways to produce formal inverses, and we don't know how to somehow select the ones that are good probabilistic meaning. So, yeah, some open question is, how do you, if, for example, if you add to the green function I showed you before any other harmonic function, you get something which is still a formal inverse of the Laplace operator, but can you make like a probabilistic meaning for it or not? And another open question is that somehow the drawing of the graph, which arises from the asymptotic of the inverses of the Kasteleyn operator or the green function, they are, we know that they are related to T embeddings in the periodic settings, but are they still related to T embeddings in the non-periodic case? This is something we don't know, and that could be interesting to define. So thank you.